Hello students. I want to do something with convolutions. What's a convolution? Okay, I'm glad I asked. So, let's multiply two polynomials. Something that happens a lot in math. So let's take 1 plus 2x plus 3x squared plus 4x cubed. And let's multiply that times another polynomial. Let's just do 5, 6, 7, 8. So 5 plus 6x plus 7x plus 8x cubed. And man, that's going to be a lot of work, right? Because I have 4 terms over there and 4 terms over there, and I have to multiply each term on the left times each term on the right. So I'm going to get 4 plus 4 plus 4 plus 4, 16 different things, and then I have to successfully add them all up. I don't like that. But suppose I just wanted to find the coefficient of x cubed. Okay. Well, I could do this by multiplying out all 16 terms, putting them all together, and causing myself a lot of grief. But if I just want the coefficient of x cubed, let's think about what I really need to do. You see, I don't care about the 1 times the 5. That's not going to contribute to x cubed. I don't care about the 1 times the 6x. That's not going to contribute towards the coefficient of x cubed. It has nothing to do with x cubed. The only way that I could use this 1 and have something that affects the coefficient of x cubed in the product is if I multiply the 1 times the 8. So that's going to be part of this coefficient, okay. What next? What about this 2x? The 2x times the 5, not going to have anything to do with x cubed. The 2x times the 7x squared, or I should say next 2x times 6x, no. 2x times 7x squared though, yes, because x times x squared gives me x cubed, so this is going to play a role. Okay, what about this 3x squared? I don't care about the 3x squared times 5. That's not going to contribute towards x cubed because that's going to have an x squared. But the 3x squared times 6x, oh yes, that does. And then finally, the 4x cubed times 5, that's going to contribute. And 4x cubed times everything else, well, that's going to be too big. So what did I get here? Well, I got 60, but that's not really what I cared about. I cared about the process of doing this, where I took the first element here and the last element here. Like, we could even think of these as lists, right? This could be looking at the list of 1, 2, 3, 4, and the list of 5, 6, 7, 8. I'm taking the first and last elements, putting them together and multiplying. Then I add that to the next element and the next from the last, putting that together and multiplying. I add that to the next and the next from the last as we've been going. And finally, at the end, I end up with the last and the first. So I'm basically doing this process where I'm taking the elements and I'm starting from the rightmost and the leftmost, and I'm multiplying each pair together and repeatedly adding them as I reverse along the way. Okay, so this is a name in mathematics. It's called a convolution, and it comes up. When would a convolution come up? Well, you just saw polynomials are everywhere in mathematics, right? So if they show up in polynomials, you know, that enough is a good reason to study them. But we actually want to use these to find the Catalan numbers. That's the application I want. Okay, what are the Catalan numbers? The Catalan numbers are a sequence that shows up a lot in mathematics because they count a lot of different things. They're perhaps not as famous as Fibonacci, but they're very famous because they pop up in so many different applications. For instance, if you have endpoints around a circle and you want to find the ways you could triangulate them, if you want to find different ways you can traverse paths, they count certain things in graph theory. They count the number of ways you can place parentheses to get possibly different values if you have a collection of variables all lined up in a row. They count a lot of things. I want to find the Catalan numbers. I've told you the Catalan numbers are important and they show up all over. We could do a course just in the Catalan numbers. Somebody wrote an excellent book, Stanley wrote an excellent book just about them We're not going to do that. I'm going to give you a formula for the Catalan numbers that involves convolutions. And that's why we introduced convolutions. Okay, so I'm telling you the 0th Catalan number is 1. And the next Catalan number is C0 times C0. And the next number after that is what I wrote there, C0 times C1 plus C1 times C0. And for C3, I'm going to start with C0, C2. You see what's happening here? Maybe you have an idea. I'm going from left to right and then moving in each towards the middle until I get to the other side. Maybe one more for clarity, just in case you need it. So what am I going to get here? Well, C0 times C3 plus C1 times C2 plus C2 times C1 plus C3 times C0. So that's how you can, one of many ways to compute the Catalan numbers. Okay, so let's try doing this. It looks like it's a great candidate for recursion because each Catalan number depends on Catalan numbers that come before it. So let's, instead of using capital C, we'll use Catalan N. And the base case, so nice here. Don't have to think. Return 1 if n is equal to 0. Okay. Now we have to complete this ternary operator. What else happens? Okay. Well, each of these things are a sum of products, but they are a sum, right? Each one of these things is a sum of things. It's a sum of products, so I'll use the sum function. Now let's see what I can do. Well, I know I'm going to have a Catalan number and a Catalan number. Let's start with this one with that I. Let's leave that blank for now. Okay, for I in range. So let's think about what this range should be. So in order to get the 4th Catalan number, I want the terms on the left to go from 0 to 3. So 0 is fine. They all start with 0, so I only need one number in my range. So what I can do here is I can just let that be range n, because what that's going to do is it doesn't include n, so this is going to go all the way up to n minus 1. So you'll see in order to get C4, it's going to go up to 3. To get C3, it's going to go up to 2. So in each case, it's going to go up to n minus 1. So very nice here. Now I have to figure out what this is, and you might be tempted to do something like that, just at first thought, because you say, okay, I want the numbers to get smaller, so let's start with n and go down. This can't be right, because what if I were to try finding Catalan 3? Well, this would start off on the right with Catalan 3 minus 0, which is Catalan 3. You can't use the Catalan 3 to find the Catalan 3. That's never going to work, because you're going to get caught infinitely searching for Catalan 3. So what I really want this to be is I want this to be 1 less than what it is. So I'll just put a little minus 1 there. And then this doesn't use the Catalan number we're finding. In order to find the Catalan number, it uses 1 less. Well, I should be pointing here. So this should work. Maybe, maybe not. Let's see. So let's find Catalan 1. That should be 1, because 1 times 1 is 1. Let's find Catalan 2. That should be 2. 1 plus 1. What about Catalan 3? This should be 2 plus 1 plus 2. So I should get 5 there. 5. Very nice. As a matter of fact, let's list the first 10 Catalan numbers. And you can see we have this nice sequence here. 1, 1, 2, 5, 14, 42, 132. And these are, in fact, the correct Catalan numbers. So, you know, the one thing I can say looking at this is it's really amazing as to how much code, or how much code we can pack into such a small place and still have it be very clear. This is a 2-line program, right? And one of the lines is just giving the function a name. And the other line, it's very easy to read. I'm going to return 1 in the base case, so if it's 0, I return 1. Otherwise, what I'm going to do is I'm going to return a sum. What sum am I returning? Well, I'm going to take the Catalan numbers from 0 to n minus 1, and from n minus 1 to 0, and multiply them together. So this is a nice example showing you the power of using Python.